Solve the linear programming problem by graphing. So we have a maximization equation. Let me show you what it is by I'm using my little pointer here. You have a maximization equation, and then you have equations from which it's subject to. We're going to ignore the last two here. It just means for all x greater than 0. So that means we're only going to be looking at, the positive x-axis, and then all y greater than 0, so the positive y-axis. So basically, if you think about it, we usually have 4 quadrants. So we're only looking at this first quadrant. And we're really going to be focused, so we're going to ignore those now. Really going to focus on just the first two equations here. And we're going to go to graphing those. And there's several different ways to graph, but we can graph by finding the x and y intercepts. It's probably one of those easiest ways to graph something. But here it's very useful for us because we need to know where the x and y intercepts are to do a good job of graphing this on. So the logistics of actually graphing it and labeling our graph correctly. Because right now we don't know how to label this graph. And once we find our x and y intercepts, then we'll have a better idea of how to label our graph. So to find the y-intercept, you let x be 0. If I let x be 0 here, then it's 2 times 0 plus 6y is less than or equal to 32. Then 6y is, and I'm not really worried about less than or equal to because I'm looking for a particular point on this line. So I'm not looking, I'm just going to say equals for right now. So y equals 7. So when I let x equals 0, y equals 7. So that means there's a point on this line that is 0, 7. So I can go ahead and graph that first. But before I go any further, I'm going to find the y-intercept. So I'll just put this up here for right now. Sorry, I'll find the x-intercept. I think, I'm not sure if I just said y-intercept. Okay, so we're going to let y equals 0. So then that's going to result in 2 times x plus 6 times 0 equals 42. And that's 2x plus 0 equals 42. And then that's just 2x equals 42. Divided by 2, we get x equals 21. So it's 21, 0. So those are the 2 points that we need to graph to plot. And then we're going to draw a line that goes through those 2 points. And that will be our first line here. Before, I do that, I kind of want to know the x and y intercepts the second line here. Because I need to know how big to make that or what increment to make my axis so that I can fit all the x and y intercepts from both lines on there. So we now can graph our first line. It's right here. We have the 2 points. We can graph those 2 points and we can graph a line through those. But before I do that, I'm going to find the x-intercepts and y-intercepts, or x-intercept and y-intercept of the second line. So I'm going to skip that step of plugging in 0. As soon as I plug 0 in for x, then, that 5x term just drops off completely. So it just becomes 3y equals 45. Then divide by 3 on both sides, and I get y equals 15. So there's this line is going to have a y-intercept of 0, 15. Now I let y equals 0, and this term is going to completely gone, so it'll just end up being 5x equals 45. Divide by 5, divide by 5, I get x equals 9. So when x equals 9, y equals 0. Those are my 2 points that I need to graph that line. So now I can go ahead and do that. And I do now know my x-intercepts and y-intercepts. I can make sure they're on our graph and can choose increments so that all of everything will be shown. I noticed that on the y-axis, my largest value is 15. I need to make sure that I choose increments so that 15 is included on there. So I think if I use an increment of 2, then on both my x-axis and y-axis, it should include both points here. I'm going to go ahead and use blue for this first equation. So it's 0 and 7. And let me just label this first because that's going to help me. This is 2, 4, um, 6, 8, 10, 12, 14, 16, 18, 20, and so on. All right, so I need for this first line, I need to graph 0, 7. So it's right here. Right, then I'm going to do the same thing for the x-axis. We're going to do increments of 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, now I can plot my point. It's at 21, 0. So it's right here. So just reiterating, I'm trying to graph this point, this line 2x minus 6y. I need to graph the 2 points 0, 7, which is on the 0x and 7 up y, and then 21, 0, which would be 21 over and nothing up. So that looks great. Now I just need to draw a line going through the 2 points, and there's my line. Now I'm going to choose green and I'm going to graph my second line. I start by doing 0, 15. So that's nothing on the X and 15 up on the Y. So that's like right here. Then 9, 0. So it's like right here. It's 9 over and nothing up. So here we go. Now I need to remember that both of these are inequalities and not just linked lines. So we can plug 0, 0 into both of them to see if they make the equations true. If 0, that way we can know which side we need to shade. Zero, 0 is clearly underneath these lines. So if 0, 0 makes these equations true, then we will be shading underneath the lines. So I plug in 0, and that's going to just be a big 0 is less than 42, which is true statement. So we are going to be graphing underneath the blue line. I mean, shading underneath the blue line. And that's going to also be just 0 is less than 45, which is true. So we're going to be graphing below the green line. So the only region which is below both the green line and both the blue line is this region here. And now the next step of this process is I need to check all the corner points of this feasible region. There's a feasible region, meaning that these are all the values. Any point in this black region will satisfy both equations here, meaning that basically, according to these equations, the and a lot of times in these problems, I'm going to think about it as these are all the possible. I have enough resources to make all the points in this feasible region. Outside of this feasible region, like a point up here, I would not have enough resources to. So this one might say I'm going to make 10 of this product and what is that, like 14 or 14 of that product, but I don't have enough resources to even do that. So it's in the feasible region that it's even possible. And then we know from a theorem that the maximum, the way to maximize this equation up here is the maximum value will lie on one of the corner points. So it's either here and look, it makes like sort of like this polygon looking shape. So it's here, 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 or here. So we must check those 4 points and see which one gives us the greatest value for our maximization equation. So I'm noticing the corner points here. The corner points are 0, 7. That was actually one of the y-intercepts for one of the lines. And then it's 9, 0 over here. And then this corner point is 0, 0. Often I don't really think about testing that point because normally it's not a maximum value of our equation, but I like to include it still. Then this point is actually unknown, and that's the inner, as you're looking at this, notice that it's the intersection of the blue and green line. And so we actually have to find that point before we go any further because we have to find all 4 corner points. So how do we find that point? Well, we could, this is for back from chapter 2. Okay, so we need to solve this little simple system of equations. And you could either do a substitution by solving one equation for y and then plugging what the equal to y into the other equation. You could do that. Or we could use the addition method where you add together the 2 equations and you get one of the variables to cancel out. So because they're both have variables both on one side, I'm going to go ahead and do the addition method. The idea there is that we want the equations to add together to cancel out either the coefficient on the y's or the coefficient on the x values. I'm just going to focus on the y values. So if I add these equations now, I would get 7x plus 9y equals whatever, 87. So notice how none of the variables cancel out right now. So what I'm going to do is I'm going to choose to multiply the first equation by -5. If I multiply the first equation by -5, then I'm going to get a coefficient of -10 on the x. Now, and then if I multiply the second equation by +2, then I'll get a +2 coefficient of x on the second equation. So watch what happens when we do this. If I multiply this equation by -5, I have to multiply every single term on both sides of the equation by -5. So it's -10x minus 30y is equal to negative 5 times 42, which is negative 210. Okay, then I multiplied this by 10x. Oh, wait, 2 times 5 is 10x, 2 times 3y is positive 6y, and then 2 times 45 is 90. So I think I'm slightly doing this different than the way I did it in the notes, but it's fine. So then I add together everything. So now see how when you add the negative 10x plus positive 10x, that equals 0x, which is exactly what we wanted to happen. Because now we can clearly see what y is equal to. So then I add together what y is, and then I get negative 24y is equal to negative 120. I divide, and then 0x plus negative 24y is just negative 24y. Equals negative 120. I divide by negative 24 on both sides. And that gives me y equals positive, I'm sorry, y equals 5. Okay, then next I just have to take one of the equations, any of the equations, and substitute back in the y in to solve for x. So do 2x plus 6y is equal to 42. So if I plug in 5 here, two x plus 30 equals 42. Subtract 30 from both sides. I get 2x is equal to 12. Divide by 2, I get x is equal to 6. So that's telling me that we have these lines are intersecting at 6, 5. And if we look at our graph, that appears to be the right point. It's right at 6 and at 5. So that looks really accurate to our graph. So now that we found that intersection, now we can check it as and see if it happens to be a maximum. I write down the equation I'm trying to maximize. And I test the point 0, 7 and see what value it gives me. If I plug in 0 for x and 7 for y, this equation gives me z equals 28. Now let's check the point 6, 5. That's 24 plus 20. So z equals 44. So far, 6, 5 is the maximum value. Gonna erase this over here. Okay, and then so the other corners are 0, 0. I'm gonna go ahead and just check that for um, just to be complete with this whole process. If this is a minimization problem, I guess this 0 would be important. 0, 0 would be important corner. Of course, that gives us a value of 0. And then 9, 0 is our last corner that we need to check. And that gives us 36. So the largest value that we could get z to be was 44. And that happened at the corner 6, 5. So we would say with, x equals 6, y equals 5, and that's what we would need to do. Have 6 units of variable x and 5 units of variable y, and that the maximum that it would give us is 44. And there you go. This is problem. Hope you found it valuable. Bye.